Hi everyone, I am Sadati from RVM Lab, King's College London, and today I present exploiting the morphology of a shape memory spring as the active backbone of a highly dexterous tendril robot, what we call ATBR, on behalf of my colleagues from University of Bristol and Clemson University. Our key contributions. We introduce a miniature active tendril backbone robot, ATBR, that you see in action here. It utilized SMA helix morphology as manipulator backbone and actuator, so it's really easy and affordable to fabricate, and local heating in response to dispersed electrical current via structural design, which I'm going to talk about more later. Possible applications: inspection, because of dexterity, and education, because it's really easy and affordable to fabricate. Working principle. Each SMA helix full turn can be a 3 degree of freedom joint by local activation of its 1/3. Here you see a helix full turn. We have 320 degrees segments, and by activation I mean passing current through that segment, and as a result Joule heating and temperature change, which causes the change in local pitch. We elongate the whole helix initially. Increase of temperature in each segment results in a shrink in the local pitch on the opposite side of the activated region, and as a result bending toward the opposite side of the activated region. We notice that by connecting a single wire to the activated region and another wire to the base of the tendril, we can get local increase in the temperature, while this configuration results passing the current through the rest of the structure as well. We suspect that at the connection point there are microsparks forming, and as a result a local increase in the temperature. We made sure that the current passing through the rest of the structure is not high enough to change the shape of the rest of the structure. Here is our setup design. You can see the activation points with double heat shrink tubes covering, and as you can see we have only 3 wires connected to them. We have an Arduino Uno and motor shield that takes care of controlling the current. We have a relay board. The relay board connects the current generated and controlled by the Arduino setup to a segment at a time. So for example, if we want a combination of the segments to deform, we pass the current through them one by one. This setup design helps us simplify the control of our electronics and also design of our control law. Modeling framework. Here you see our ATBR setup again. Every section here is consisting of an active section and an inactive section. For a section transformation, we write Tm equal to Tj.tl. Tm is the section transformation, TL is the inactive section fixed length transformation, and Tj is the active section constant curvature kinematics. Active section constant curvature parameters are backbone length, polar direction of the bend, and the bending curvature. As you can see here, 3 wires are connected to each active section and a single wire is connected to the base of the tendril. We want to relate the change in local pitch to the constant curvature parameters here. So we introduce 3 imaginary tendon lengths. These tendons are placed with 120 degrees offset on a circle with radius equal to the tendril cross-section radius. Any change in the local pitch results in a change in the length of these imaginary tendons, and as a result, the change in the constant curvature parameter of that active section. The section imaginary tendon length are simply the change in the local pitch subtracted from the initial tendon length. SMA Properties Identification. First, we tried to find a relation between the temperature and the change in the pitch, for which we used a laser thermometer. These graphs show the relation between temperature and change in the pitch, time versus temperature change, and time versus change in the pitch. As you can see, the plots relating the temperature to time or the change in the pitch doesn't provide reasonable trends, but the plot for time versus change in the pitch shows an almost linear behavior to which we can fit a line with a specific identified formula. We use that as our local pitch control law. For that, we set the current to be constant, in this case 1 amp. We assume the actuation time is our control input or control variable, and we assume some correction factors to be identified for each joint to increase the accuracy of our model. Here is the equation for the fitted line that relates the change in the pitch to the activation time. And having a look at the second line, you see C1 as the correction factor for the slope of this line, and C3 as the correction factor for the lag in the activation of the segment, which is because of the thermal lag of the material. Here you see the identification process for the change of pitch versus time and temperature. And here you see the identification process for individual segments of each joint. As you can see, we have 5 joints and we have 3 segments in each. Doing these experiments, we could form this table for the correction factors associated with each segment of each active section or active joint. Also here you see the number of inactive turns for each section. Then we did some experiments on the overall performance. Here you see simple bending, and here you see axial contraction of the manipulator. And then we did some random complex configuration tests. You see the activation of each joint one by one until we reach our desired final shape. Here you see a comparison between the modeling framework and some complex shapes achieved by random actuation of different segments in different joints, for which we have good agreements. But it's worth mentioning that in the current study, the activation time values are estimated. And we tried to showcase some sample confined space navigation. A pathway is drawn on a piece of paper. We didn't use physical walls to avoid any physical interaction, and as a result, bending of the passive bending of the backbone. So what you see is controlled active bending of the segments, one by one. Limitations and future study. At the moment, we have to manually set the initial shape of the tendril after each actuation. We're going to address that by having two opposing coaxial tendrils. We're going to do detailed variable curvature kinematics, payload study, and sensitivity to ambient temperature analysis. Also, a detailed error analysis of modeling and control framework. Thank you for your attention.